In this video, we're going to do some curve sketching. So we're going to begin with an example where we know the function's a continuous function, so it doesn't have any jumps or asymptotes or anything like that. We don't know the equation for the function though, we just know some information about it. Okay, so some information about the function with some information about the derivative of the function and some information about the second derivative of the function. Okay, this is much of the information that we would need to find if we had the equation instead of all of this. So we're going to go box by box and try and figure out what each of these things is telling us. So let's start with this box here. So it says the function evaluated when x is -5 equals 4. So that means the y value at x equals -5 is 4. So this box is giving us some points on our curve. So we can plot these points. So at -5, 1, 2, 3, 4, 5, 1, 2, 3, 4. I have y equals 4. Okay, so this is -5, 4. At -2, I have y value 7. So I get a point at -2, 7. And at 3, I'm at -2. So I have a point down there. So I've already have 3 points on my curve. So I know that I have to go through these 3 points. Now, what is the next box telling us? So it says the limit as x goes to plus or minus infinity of our function is equal to 2. This is telling us that we have a horizontal asymptote. So y equals 2 is a horizontal asymptote. Okay, so I can sketch that on my graph as well. So I'm going to put a little dotted line here for y equals 2. And because it's as I go to plus and minus infinity, I know as I approach from minus infinity, x goes to minus infinity, I'm going to approach this line. And also as x goes to infinity, I'm going to approach that line. So I want to make sure that I indicate that. Now, the next box here is telling us f prime of -2 equals 0 and f prime of 3 is undefined. So what this is, these are our critical numbers. So x equals -2 and x equals 3 are critical numbers. So remember how you find critical numbers, you want to know where is the derivative 0 and where is it undefined. Okay, so and because these are all in the domain, they're critical numbers. Now because f prime of 3 is undefined, but we're continuous there, we're likely going to have a sharp turn. Okay, so we should be expecting a sharp turn there. This next box is telling us the second derivative at -5 is 0, and the second derivative at 3 is undefined. Okay, so these are possible inflection numbers. So x equals -5 and x equals 3 are possible inflection numbers because that's where the second derivative is 0 or undefined. Okay, now over here on the right we have these tables. So the first table here is talking about the sign of the first derivative, and notice that the intervals are split at our critical numbers. X equals -2, -2, and x equals 3. So that's where we split. And then it's telling us the sign of each in each interval of the derivative. So remember, -2 and 3 are the only places where it might switch. And in fact, it does switch at both. Okay, so because it's positive, we know that it's increasing on that interval. And then it's going to decrease on the interval from -2 to 3 because it's negative. And then it's going to increase again. So we can see that at -2, we're going to have a relative maximum. And at 3, we're going to have a relative minimum. Okay, so I'm just going to note that. So up here, this is going to be a max. And at x equals 3, this is going to be a min. Okay, so we know that already. Now, the next table is for the second derivative. And notice again, it splits at our possible inflection numbers, because those are the places where it might change. So we split at -5 and we split at 3. So if we're positive, that means we're happy, we're concave up. If we're negative, we're concave down. Okay, so notice that it switches only at -5. So this is our only point of inflection. Okay, so we know that this point here, I'm just going to abbreviate it, POI, is a point of inflection. So the concavity changes there. At x equals 3, though, it doesn't change, so that's not an inflection point. Okay, so we didn't get a lot more information that we can sketch immediately, but what I'm going to try to do down here in the bottom is combine these intervals. Okay, so the first thing we do, the first place where we change something is at -5. Okay, so down here, maybe let's do it in blue, from -infinity until -5, okay, we were increasing and concave up. So what that means is we're going to have a shape that's like this. Okay, so this is a summary of what's up top. Okay, and then this is the shape that we're going to have. So combining those two, we get this shape. So that means that our graph, we know that we're approaching y equals 2. So it's probably going to look something like that. Right? So it's concave up and it's increasing. Now, the next place where something changes is at -2. Okay, so from -5 to -2, that's going to be this part here. We're still increasing, but now we've switched to concave down. So that means our shape is going to look something like this now. Okay, so now I want to try and draw that. So I'm switching at this point to concave down. Okay, so maybe I did that a bit too dramatically. So it's going to be something like this. And now we know that at -2 we have a relative maximum. And it's one where the derivative is 0. So the slope here, this is a nice smooth maximum. Okay, so the slope here is 0. It's down here, maybe I should have written this. This is a relative min. Okay, but remember we thought it's going to be a sharp turn because the derivative doesn't exist there. Okay, so we've got part of our graph. Now, the next place we switch is at 3. Okay, so I'm going to go, my next interval is going to be from 2 all the way to 3. So now I'm going to be decreasing on this interval and concave down. So my shape is going to look something like that. Okay, so when I go up, I'm going to have, so it's a nice smooth thing up here. Oops. Didn't have my hand in the right place. So it's a nice smooth thing up here. And then I want to go all the way down to this point here in a concave down manner. So notice if I dump water from up here, it's just rolling off. Okay, it's not collecting. Over here is collecting. Okay, this is concave up shape. Okay, but all of this is concave down. And then the last bit, the last interval is 3 to infinity. Okay, so on this last part, now we're increasing, but we're still concave down. So I'm going to look something, my shape is going to look something like that. Okay, and I know this is a sharp turn, and I know that I'm going to approach y equals 2. So it has to be something like that. So we're concave down, but we're increasing. So we're going up as we move to the right. Now, I don't know if this concerned you at all, but it shouldn't. Okay, so this sometimes freaks people out. So we crossed this horizontal asymptote. This is actually okay. So the horizontal asymptote only tells you what happens when x is really, really big or really small, okay, really big negative. It doesn't tell you anything about when x is sort of near 0. So sometimes near the origin, you can cross these horizontal asymptotes. So the vertical asymptote you never cross. Okay, that point is not in the domain, but the horizontal ones it's okay if you cross. So if your graph needs to cross it, just go through it. It's probably supposed to. If we had the equation, we could figure out where it crosses by setting our function equal to y equals 2 and solving for x. Okay, but here we don't have the equation, but we know it's continuous, so there cannot be a jump here. Okay, so to get from here to here in a continuous way, I'm going to have to cross through this point. Okay, that's the intermediate value theorem, actually. So that's our sketch. So that was when we had all the information. Now let's try one where we have the equation and we have to do all of the work. So the first thing we want to do is think about the domain. Okay, so what is the domain for this function? Well, it's a polynomial, and polynomials exist everywhere. Okay, so our domain is all real numbers, and we know our function is continuous. Okay, so we're not going to have any weird jumps or anything like that. Okay, so we know it's a polynomial, so it has full domain and is continuous. Now, so that's one thing. Okay, what about the intercepts? Okay, so what if we want the y-intercept? We would set x equal to 0. Okay, so that means that y is equal to 4 times 0 cubed minus 0 to the 4th. Okay, that's just 0. So we get a point at 0, 0. Okay, this is also an x-intercept. Okay, but let's see if there's any more x-intercepts, because there could be. We want to set y equal to 0. So that means I'm going to have 0 equals 4x cubed minus x to the 4th. So now I want to factor, so I can take out x cubed, and then I'm going to have a 4 minus x. So I have two things multiplied together equaling 0. So that means one of them has to be 0. So either x cubed is 0, or 4 minus x is 0. So if x cubed is 0, we get x equals 0, which we already have. But we also get x equals 4, if 4 minus x is 0. So I'm going to have another point, so another intercept value is at the point 4, 0. Okay, so we have 2 points now on our curve. That's nice. Okay, now the next thing that we're supposed to think about is the vertical asymptotes and holes. So does this function have any? Well, vertical asymptotes and holes only appear when there's x values that are not in the domain. But here we have a nice continuous full domain polynomial. So that means we're going to have none of these. Okay, we don't have to worry about those. Now, horizontal asymptote is slightly different. Okay, so here we want to think about the limit as x goes to plus or minus infinity. Maybe I want to do these separately. So let's say we go to plus infinity of our function f of x. So that's the limit as we go to infinity of 4x cubed minus x to the 4th. So we could, so when you're taking the limit as x gets really big for a polynomial, really the only thing that matters, okay, well this, we could actually do it, I'm just trying to think of a way to explain this best. So you could think about this as over 1. No, I don't want to do that. So, okay, when you have a limit as x goes to infinity of a polynomial, it's really only the biggest power of x that matters. So if x is going to infinity, okay, this thing's really big. But this thing is so much bigger. It's a factor of x bigger, and x is infinity. So it's going to be so much bigger. Okay, so this limit is actually going to be equal to the limit as x goes to infinity of just the biggest power, so x to the 4th. Okay, now if x is really big, x to the 4th is really big, so I'm going to have a negative really big number. So this is going to go to negative infinity. So not a number, not an integer. Similarly, if I go to negative infinity, the same sort of thing happens. So I have 4x cubed minus x to the 4th. So because x is very large in magnitude, it's only the biggest power that dominates. Okay, but now I'm going to negative infinity. So what happens when I put a really big negative number in for x? Well, I'm going to have negative a big number to the power 4. That's actually going to make this number positive, and then I'm going to have a negative out front. So again, I'm going to go to negative infinity. Okay, so this tells us lots of information. So as x is getting really big from positive infinity and from negative infinity, the y values get really, really small. They're going to negative infinity. So first of all, we know that there's no horizontal asymptote because they approached, because they didn't exist, these limits. Okay, but we also know that the y values are getting very small, so we can show that in our graph as well. Okay, the next thing we're supposed to check is symmetry. So we want to check for even and odd symmetry. Let's do this in blue. So we're going to consider f of negative x. Okay, so this is going to be 4 times negative x cubed minus negative x to the power 4. So when I cube a negative x, I'm going to get negative x cubed. So this is going to be negative 4x cubed minus, and then when I take a negative x to the 4th power, I just get x to the 4th power. So the negative goes away. So this is not equal to f of x, okay, which means that it's not even symmetry. And it's also not equal to negative f of x. So that tells us that it's not odd either. Okay, so we don't have any symmetry here. Any of the symmetries that we check for anyway. Okay, so now where's the calculus come in? So now we want to think about all the stuff related to the first derivative. Okay, so that means I want to calculate the first derivative. Okay, so our function is 4x cubed minus x to the 4th. So that means our derivative is 12x squared minus 4x cubed, which we could simplify to 4x squared times 3 minus x. Is we factored it. So we want our critical numbers. Okay, so we take our derivative and we set it equal to 0. So that means 4x squared times 3 minus x should be equal to 0. So that means that x squared is equal to 0, or 3 minus x is equal to 0, which means that x is 0 or x is 3. Okay, these are critical numbers. okay, because the derivative is 0 there. We should also think, okay, where does the derivative not exist? Okay, but here it's a polynomial, so it always exists. So we don't have anything like that. We probably want the y values. Okay, so maybe I should write. Okay, so at x equals 0, the y value we actually know is 0. Okay, so we get critical point of 0, 0. Okay, we already had that point above because it's an x and y intercept. But when x is 3, the y value is going to be 4 times 3 cubed minus 3 to the power 4, which is 27. Okay, so that gives us another critical point is 3 and 27. Okay, so what else can we do with the first derivative? Well, we want to find where the function is increasing or decreasing. So we're going to make our number line. Okay, and we're going to put on 0 and 3. Maybe I should move 0 over a little bit. Okay, so these are the places where the derivative might change. So now I want to test a point, so maybe I test -1, something that's less than 0. So f prime of -1, what does f prime look like? Well, it's 12x squared minus 4x cubed, so here. I prefer to use the factored form, so I'm going to use that. So this is going to be 4 times -1 squared times 3 minus -1. Now, I don't actually care to compute this number, but if you want to, it looks like it's going to be 16. But basically, I have a positive. The 4 is positive. -1 squared is positive, and 3 minus -1 is also positive. So if I multiply 3 positives, I get a positive number, which means that I'm going to be increasing on this interval. Okay, now I want to check something between 0 and 3, so maybe 1. So f prime of 1 is going to be 4 times 1 squared times 3 minus 1. So again, I have a positive times a positive times a positive. So I get a positive. So I'm still increasing. Now something bigger than 3, maybe let's try 4. So f prime of 4 is going to be 4 times 4 squared times 3 minus 4. So it's a positive times a negative, because 3 minus 4 is -1. So two positives are positive, and then I times by a negative. Here I'm going to get a negative, so that means that I'm decreasing. Okay, so now I can use the first derivative test to classify these critical numbers. So when I increase, and then increase again, I did not change. So that means that this critical number is neither a max nor a min. Okay, so it levels off there. The derivative is 0, but then it increases some more. So it's not a max or min. But at x equals 3, I increase and then I decrease. So I'm going to get a maximum here. Okay, so this point is going to be a relative maximum. Okay, so that's our point at 327 is a relative max. Okay, so continue on. So now I want to think about the second derivative. Okay, so our first derivative was 12x squared minus 4x cubed. So we take the derivative again. And I actually didn't really want to do this in purple, but okay, that's fine. So f double prime of x is going to be 24x minus 12x squared. Okay, so if I factor that, I can take out 12x, and I'm left with 2 minus x. Okay, so then we want to find our possible inflection numbers. So I take my second derivative, set it equal to 0. So that means 12x times 2 minus x is equal to 0, which means that x is 0 or x is 2. Okay, so these are possible inflection numbers. Okay, now again, we should get in the habit. Where does the second derivative not exist? Okay, these are also viable points, except our second derivative is also a polynomial, so it always exists. So we don't have to worry about that. Okay, so we're probably going to want to plot these points. 0 we already know is at 0, 0. So I want the y value when x is 2 so that I have this point. So the y value is going to be 4, was it 4? Yeah, 4x cubed, so 4 times 2 cubed minus 2 to the power 4, and I think I get 16 if I do that. So we have another point at 2, 16. Okay, now we want to see, is this an inflection point, or are either of these inflection points? So we'd make our number line, put on 0, put on 2. Okay, now we want to check a point, check in the second derivative now. So if I do negative 1 into our second derivative, it's 12 times negative 1, 2 minus negative 1. So this is a positive times a negative times a positive. That's going to be a negative, so we're concave down in this interval. Something between 0 and 2 is 1, so I plug that into the second derivative. So it's 12 times 1 times 2 minus 1. So it's a positive times a positive times a positive. So here's a positive. That means that we're concave up. And then something bigger than 2, so let's say 3. So f double prime of 3 is going to be 12 times 3 times 2 minus 3. So that's a positive, and a negative. So that's going to be a negative, so we're concave down there. So we have a point of inflection at actually both of these because it switches concavity. So now I just want to try and draw our function. Okay, so we know it goes through 0, 0. At 2, we're at 16. Okay, I'm going to put that around here. At 3, we're at 27. Let's put that way up here. We know that's a maximum. And then at 4, we're back at 0. So those are our y-intercepts. This is 4, 0. And then from all the way to 0, we know that we are increasing and concave down. So we're going to have this type of shape. From 0 to 2, we're increasing but concave up. So we have that type of shape. From 2 to 3, we're getting kind of tight here, but we're still increasing, but now we're concave down, so we're back to this shape. And then after 3, we decrease, and we're concave down, so it's going to have that type of shape. So our graph, and in fact, we know that as x goes to negative infinity, the y values get small, and as x goes to positive infinity, the y values get small. So we're leaving these directions. So what this is going to look like, we're concave down, we're going to approach this point here, and it levels out, but then it keeps increasing, but now it's concave up until this point. and now it switches to concave down, which is kind of hard to do because it's so tight, but switches to concave down, and then it's decreasing but concave down the rest of the time, goes through the decreases very quickly. I shouldn't have stuttered like that, but it's going to look something like that. Okay, so this is our function. We have a point of inflection at 2 and at 0. Here, the derivative at 0 is also 0, so see it, that's why it levels out. And up here, we have a relative maximum with the derivative as 0. So it's not a sharp turn, it's a nice smooth turn. So that's what our function looks like. So there's one graphing example from start to finish.